So one more time, good afternoon to all of you. Good morning to all of you. So today I want to start this integration. We studied certain functions which are bounded, then we can find their integrals. But improper integrals are basically the integrals where the function may not be bounded. It not necessarily bounded function, and or in the other case, the interval over which the function which we are integrating, that may not necessarily be the finite interval. So let us see first of all what is the what we are looking at. So this particular definition, this particular area formula, we know that if we integrate a continuous function over closed interval AB, then the end area under this function f over the interval closed interval AB is exactly the integration a to b ft dt, and that we can write as a limit of the small interval a to x. So this particular area is the area of the function over the interval a to x, so that we are considering here. And then when x approaches to a, we will get the exact integral formula of the entire closed interval, area of the function over the entire closed interval. So this formula we already know, and we can observe this by the graph itself. So the question is, can we extend this formula for the interval which is infinite? So the interval is starting from x equal to a to infinity. So to observe this particular formula, let us see one particular example of a function. So if I take the function which is a kind of step function, which is defined from interval 1 to infinity to real numbers, and that function takes value in this way, that x equal to 1 is f of 1, value x equal to 2 is f of 2, right? That is this value, and so on. So question is that what will be the integration of ft dt in this case. So that is basically the area below this function over the interval 1 to infinity, right? So from the graph itself, we can see that this particular area over the closed interval 1 to 2 is forming a rectangle. So this area, the length is 1 here, and on the other side the length is f of 1. So first area, this area will be nothing but f of 1 into 1, so that is f1. The same way, this area will become f of 2, right, and so on. So the entire area, we can observe that it is f of 1, that is area above the closed interval 1 to 2, plus f of 2, and so on, right, from the graph itself. Now if I call this f of 1, that is a real number, to be a1, f of 2 be a2, and so on, then what will be this sum? Now this is an infinite sum of real numbers. So that is we already studied in this course, that is called the series, and simply we can write it as k is equal to 1 to infinity ak. right? And then we know that if the series converges, if and only if we write it as a limit of the partial sum, right? So that is exactly the this is the formula of the nth partial sum. And on the other hand, when we go backward, then what is this sum? This is sum of the first n numbers, a1 plus a2 plus up to an, that is f1 plus f2 up to f of n summation, and that will be nothing but the area of the function on the closed interval 1 to n, right? So this is nothing but limit n tends to infinity 1 to n ft dt. So what we are discussing here is basically the motivation of this, the definition, how we define the integral over the infinite interval. So that is here, because it is a series and the step function, we are taking the limit in terms of n. But now in general, we will take the limit over the variable x itself. So this is just a motivation. Now we'll start with the proper definition of improper integral, and then we'll take some examples. So definition of improper integral of first kind. So there are basically two types of improper integral. First, we are discussing the first type of interval, first type of improper integral. So that is over the interval a to infinity. A is any real number. So integration a to infinity is defined as limit of x tends to infinity a to x ft dt. So you can see that this is same as this formula, but I have now replaced n by x here, right? And we will write this integral as a limit x tends to infinity whenever this limit exists. So to find such an integral, first thing is that function should be integrable over the interval x to a to x. That is the first condition. If the function is not integrable, we cannot find the integral over a to x. And the second condition is that this limit should exist. Then if this limit exists, that means it is a real number, then we say that the integral a to infinity is convergent. So first thing to note here is that here the function need not be non-negative. Right? Because when we discuss this area, we have considered the functions to be non-negative because we can represent it in a diagram. But in general, the function need not be non-negative. So if this limit exists in the case of, so in this case we say that in the case of this limit exists, we say that the function the integral a to infinity ft dt is convergent. All right. So there are two possibilities: either this integral is convergent or it is divergent. All right. Otherwise, we say that the integral diverges. So let us see some examples when the integral converges and when the integral diverges. The first example is that is known as test functions. So this example is important because it will help us to use certain tests. So in infinite series, we have seen that there are certain tests, which is a comparison test, limit comparison test. So since this improper integral of first kind is related to the series which we have just discussed, so there are similar tests for this type of integrals also. So there, these examples will be useful to identify the integral is convergent or not. So let p be any real number for which values p, the integral 1 to infinity 1 of t power p dt converges, and for which values it diverges. So let us try to solve this question. So since our integral is integration over 1 to infinity, so we will use this particular formula of improper integral, right? So a is 1 here because we are integrating over 1 to infinity, and whatever function we are integrating, that is our f of t. So first thing is, let us write down the formula. So that is integration 1 to infinity ft dt is limit x tends to infinity 1 to x ft dt. So here, which function we are integrating? We are integrating the function 1 divided by t power p. So that is our function f of t. So here f of t is 1 upon t power p. So we want to first integrate the function over the interval 1 to x, and then we will see whether this limit of this integral as x tends to infinity is convergent or not. So let us first find out what is the integral. So integration 1 to x ft dt is integration 1 to x 1 upon t power p dt, right? And then we know that 1 upon t power p, that is t raised to minus p, so its integral is t raised to minus p plus 1 upon minus p plus 1, and limit is 1 to x. So this depends on the value p. So there are two cases, either p is equal to 1 or p is not equal to 1. So if p is not equal to 1, then this is the integral, right? Because if p is 1, then it is the integration of function 1 by t, and then we know that integration of 1 by t is natural logarithm of t. So if p is 1, then the integration is log t, and the limit is t is from 1 to x. So this is limit of t. T is from 1 to x. So if we substitute the limit, then the first integral in the case of t is not equal to 1 will become x power minus p plus 1 minus 1, right? Divided by 1 minus p. And on the other hand, we will get log x, natural logarithm of x. So this is what we have found, this particular integral. But now we have to find the limit of this to get this integral, right? So therefore integration 1 to infinity ft dt is limit x tends to infinity integral 1 to x, and that is same as limit of both of these cases. So that is limit x tends to infinity x power minus p plus 1 minus 1 by 1 minus p if p is not equal to 1, and it is limit x tends to infinity logarithm of x if p is 1. So now we know that if we take limit x tends to infinity logarithm, then logarithm is an increasing function, so it goes to infinity. It is a monotonically increasing function, and on the other hand, the limit x tends to infinity of this function will be 1 upon p minus 1. So this integral is equal to 1 upon 1 minus p if p is greater than 1. If p is less than 1, then also this limit does not exist, because if p is less than 1, then x so 1 minus p is greater than 1, greater than 0, and then x raised to 1 minus p will goes to infinity as x goes to infinity, right? So therefore for p less than 1 also it diverges, so that case will come here. So for p equal to 1 also diverges, p is less than 1 also diverges. So in both the cases the sequence diverges. So what we finally got is the integral. Therefore the integral 1 to infinity 1 upon t power p dt converges to the number 1 upon p minus 1 if p is greater than 1, and the integral diverges if p is less or equal to 1. So this result is more or less same as the result of p series test. So if you remember the p series test, then summation 1 upon n power p converges if p is greater than 1, and summation 1 upon n power p diverges if p is less than equal to 1. Alright, so this result is analog of this particular result, and then we know that when we discuss the convergence of a series, we use limit comparison test as well as comparison test using this particular series, p series. We compare the given series with the series summation 1 upon n power p, and then we check whether the given series is convergent or divergent. So same way for the improper integral of first kind, that is a integral over 1 to infinity of the given function, we will use a comparison test and limit comparison test using this particular result. So for example, if we special case, what we get is for p equal to 1, so p equal to 1 case will come here. In that case, the series is divergent. The integral is divergent. So p equal to 1, what we get is 1 upon t power p, p is 1. So that is 1 upon t dt is divergent. Here directly also you can compute this integral using the definition, and that is exactly what we verified in the previous example. And another is for p equal to 2, the integral 1 upon t power p will become 1 upon t square is convergent. Right? But every time it may not be easy to conclude this. Sometimes it is easy, sometimes the function may not be integrable, so we cannot find even limit. So let us take some different types of examples. So the question is integral 0 to infinity sin t dt convergent? So once again we'll apply the formula itself. So if we apply the formula, it is integral 0 to infinity sin t dt. So a is 0 here because integral is from 0 to infinity and the function is sin t. So by definition it is limit x tends to infinity 0 to x sin t dt. And then we know that the integration of sin t is minus cosine t. The value is t is equal to 0 to x, limit x tends to infinity. So that is limit x tends to infinity 1 minus cos x, 1 minus cosine of x. Now here what we want to find is, we know the graph of the cosine function. So question is whether we can find limit x tends to infinity of cosine function. So from the graph itself we can see that this function oscillates. So since it is oscillating, this limit does not exist. This limit does not exist. From the graph of cos x, since the cos x is oscillating function, we can see that this limit does not exist. So either the limit does not exist or it goes to infinity. Both the cases we say that the integral is divergent. So therefore this integral diverges. One more example I want to take is a simple one, that is e power minus x. So 1 to infinity e power minus t dt. So if this function is convergent or not. So this also is a very simple example you will be able to do. So this is 1 to infinity e power minus t dt is limit x tends to infinity 1 to x e power minus t dt, and then we can integrate this function. So integration is minus e power minus t 1 to x. So we have to be careful with the sign. So when we substitute above limit, it is e raised to minus x, then minus of so let us take from 0 to infinity. For simplicity, we are taking the integral from 0 to infinity. So in that case, what we will get is we'll get plus 1, right? And now as x tends to infinity, by e power minus x is 0, so the integral is 0. So therefore this integral converges. So in fact we could have taken the integral from 1 to infinity also. In that case we'll get the limit to be e, right? So in that case also it converges. So now these are the basically test functions, whatever we discuss, the e power minus t and the summation 1 upon t power p. Let us see a limit comparison test. First of all, the comparison test. So if you remember the statement, for comparison test we have taken both the series to be non-negative number series. So same way here we are taking the functions to be non-negative over the given interval. T greater than equal to a, and if the integral the right side integral, if it is convergent, then the left integral converges. So can anyone say what happens if the left integral diverges.
The right integral will also diverge.
Right integral will also diverge.
Very good. So whenever so we can use this result in the other way, and that will ensure us that the left integral diverges, then the right integral. That left integral means integration ft dt diverges, then integral gt dt is also diverges. That is coming from this theorem. So we usually use this theorem. We usually compare with the test function. So test function is 1 upon t power p, and sorry, the integral, and the other test function is e power minus t. So depending on which function is given, based on that we use this comparison test. So first example is that does the integral 1 to infinity cos square t by t square converges. So just we can't say yes or no, we have to justify it also, we have to give explanation also.
So we can use 1 by t square to see
Right.
that the function converges.
Yes. So how did you guess that 1 by t square?
Because cos square lies between 0 to 1, so 1 by t square is greater than cos square. Sorry, 1 cos square t by t square.
Right. So you're absolutely right. So here we can see that the function is in terms of cosine function. So usually in these methods we apply kind of squeeze idea. So like squeeze theorem. So whenever the function is given, whatever function is given, we can first try whether we can squeeze that. If I squeeze this function, we can see that since the cosine value is between minus and 1, cos square value is between uh, 0 and 1, as he said, and that is the exactly this observation. Using this observation, we can see that we can compare, we can try to compare this series, this integral with the 1 upon t square. So, so first of all, note that the function is non-negative. That is the first criteria of the theorem. The function ft to be cos square t by t square is non-negative. So let the function gt to be 1 upon t square using this idea, and then we know that since 0 less than or equal to ft less than equal to gt for every t on the integral area. So integration is over 1 to infinity. So therefore we have to verify this condition for all t greater than equal to 1. So this should be satisfied over t greater than equal to 1, that we can see. And then now since the integral gt, what is this integral? That is integral 1 upon t square dt. So whether it is convergent or divergent. So this is actually convergent because in that p integral test, p is equal to 2. So whenever p is greater than 1, it is convergent. So since this integral is convergent by comparison test, integral ft is also convergent. So right. So this is exactly the solution. So if you remember, whenever we have a series, every time we cannot find the sum of the series. We say only that the sum is a finite number. It is convergent. The same way, every time we cannot find the integral of the function over 1 to infinity. Sometimes we can find, like in the test function example, we have actually find the integral is 1 upon p minus 1, but every time we cannot find. So here also we are saying the integral is convergent. We are not actually finding the area. Okay, so let me just one exercise which you can try. So whether this integral minus x square dx is this convergent. Okay, so I think this would be enough for today, because you may have lecture also after this.